Okay, good evening, everybody. We'll start. Khaled, if you can take attendance, please. I sent you an email an hour ago asking you to read a paper. Did you read it? Okay, good. All right, so let's start by sharing the screen. So as usual, let's start with asking how are you doing this evening? Great. All right, so I asked all of you to read this paper titled Self-Assembled Monolayer Organic Field Effect Transistors. And intentionally, I removed any information about the authors, affiliations, and so on. And based on this, I would like to ask a few questions now. So if you can respond, I'm going to ask you 8 questions about this paper and use your iPhones or other phones just to answer those questions. So do the authors state the problem clearly? What is the problem they are trying to solve? Well, I'm looking for participation. I hope that we'll get more responses than only one. But at least one of you think that the authors mostly answer the problem they're addressing. Not very clear, mostly. 3-terminal transistor out of molecules. Any other comments? Okay, so let's move to the next question. Do the authors give a good historical overview of the problem? So they really don't put the work in the historical context. That seems to be the consensus. Okay, let's move to the next question. Do the authors explain well their hypothesis? You can elaborate, explain a little bit. No response to this question? A little vague. Well, I think the hypothesis is that if you construct a three-terminal device out of this molecular transistor, it should work. So the question is it working or not? That's basically. Technically. Yes, I did, but not clear. Okay, let's move on. Do the authors explain well their approach and methods? Maybe to an expert. Yes, regarding the fabrication. Hopefully, but not concise. Okay, let's move on. Do the authors explain well their novel contribution towards solving the problem? Not sure. No. Okay, let's move on. Do the authors perform adequate control experiments? I know you think yes. Another thing that they don't really talk about this. Can't comment. Okay, next. Do the author explain well what was learned? How did they move the field forward? At the end of 4 seconds, so short. Okay. At the end, feel separate from the paper briefly, yes, but the conclusion, not very sure. Okay. All right. Okay, so let's stop the Mentimeter and move to our presentation. Everybody can see the presentation? Okay, so we answered those 8 questions. Let me do this very quickly. Yeah, they do state the problem beginning. They kind of given the historical overview, but very brief. Do they explain their hypothesis? Yes, they are going to test for gain in the 3-terminal device. They give enough details for 6 organic molecules, the biofabrication measurements. Do they explain their statistical analysis? They have 1 sentence on this. Similar behavior has been observed for many devices giving statistical relevance for this data, but they don't really give statistics, error bars, and so on. Do the authors explain well their novel contribution towards solving the problem? Yes, promise of molecular electronics on the nanoscale. Do the authors perform adequate control experiments? They do control experiments with non-conductive molecules, but they don't show the data. And do the authors explain well what was learned? Novel, small, fast, cheap electronics. Very brief comments, but they do. All right, so we have, I think, 11 questions that we ask ourselves whenever we analyze papers, and 8 of these are, I would say, reasonable. This paper went through peer review, it was accepted for publication, and I think that most of the answers to these questions are reasonable. I'll skip these 4 last questions, and let's move into the data. So these are 2 images from 2 different papers. Figure number 2 is from the paper you read, and figure number 3 is from a different paper analyzed on different molecules. And see what happens when I overlay basically figure number 2 from our paper to figure number 3 from another paper by the same authors. So what I'm going to do now, I'm going to get out of the presentation mode and just see when I scale figure number 3 from another paper, look at this curve, and most importantly, look at this curve. What can you tell me about? You can open your mics and respond. Any thoughts? Yep. And now look at this curve. Not all the data points. Here there is deviation, but the rest. Let me give you another example. Still a paper from the same authors. Here are 3 different papers, 3 different graphs, and I'm going to do the same trick. I'm now overlaying those 2. at this curve here. Now look at this one. And look at this one. Just playing with basically the scale. Okay. And this is, again, two different results and two different graphs. Any thoughts, any comments so far?
Yes. With those two figures, even the noise on the upper one is the same.
Yes.
It's like data manipulation, complete manipulation.
Okay. So this is a topic of our today's presentation. It's called the Sean scandal. I didn't want you to search and read about this because I'm going to give you a full account of what happened. Really, really interesting story. And it seems like there is a new story developing that is similar about the Alzheimer, and I asked some of you to look into this. But the Sean scandal is considered to be maybe the biggest scandal in physics, fraudulent science ever. So this is example for scientific misconduct, and that's the topic of today and next week meeting. Just to tell you that, you know, obviously the Sean scandal is very famous. It's a, you know, there is, you can watch YouTube movies. There is a book. There are lots of stories about that scandal. That was such a big scandal. But scandals happen all the time, even today. So here is a new scandal. It seems like it's a scandal in February of this year. A guy who developed a technology to test food supplements by looking at DNA sequencing of food supplements was very, very famous for developing this technology and started a company and became very rich very quickly. His name is Stephen Newmaster. And it seemed like there was an issue with many of his papers, and that was reported in Science in February of this year. But the story did not develop to be a full scandal. In June of this year, the guy was kind of cleared, but you are welcome to read this piece here in Science in June. He wasn't really clear. Usually when there are suspicions for such fraudulent misconduct, the university is basically in charge of setting up a committee to test and look very carefully into the case. In this case, the university committee cleared the guy, although they probably did not do a good job. And there is actually many cases of fraudulent data in this guy's papers. So this is an interesting read, and if anyone is interested, you can take this as an example to develop your paper on. And we mentioned already the case of Alzheimer. This is reported for the first time in July of this year. Turns out that the paper that all the big pharma and huge amount of science that was done since on protein tau, being basically the culprit in Alzheimer's disease, the very basic data done by gel electrophoresis in a paper by this guy here, I forgot his name, turns out that the gel electrophoresis data that was published in the original paper were fake. There is a paper by this guy, Matthew Shrug, who for several years, he investigates the work, and then he goes to a lady named Elizabeth Bick, who is expert in looking at manipulated images. And the story started to surface in July of this year. A really interesting twist to this story came out this month. It turns out that the guy, Matthew Shrug, who was a whistleblower, for this story about the protein tau as in charge of the Alzheimer's disease. He himself is a co-author as a student when he was a young student. He's a co-author of a paper that is also suspected in misconduct. It's not his misconduct, it's his mentor. But really, really interesting story, a twist to the story. The guy has spent many, many years in investigating the story of Alzheimer's, and it turns out that during his PhD, he wrote papers that are also involved in misconduct. So this is a huge story, and I welcome you guys to choose the story and really dive deep into the story and tell us about it. But today we are going to discuss the short story. All right, so I'm going to give you an historical overview. I'm going to use several different references, and one of these references is a very close friend of mine, and I witnessed when I was in Berkeley, I witnessed the story developed. It was a huge shock for the whole community. So let's go step by step. We are going to, let me just remove this bar for a second. Okay, yeah. All right, so we are going to go mostly by Doug Natelson's recollection of the story, and here and there we'll use some other additions. This is an account for the state of AT&T Bell Laboratories, or at that point it was called Lucent, at the late 90s and early 2000s. Personal note, I myself did my postdoc at AT&T Bell Laboratories in the late 80s, beginning of the 1990. So we are talking about 10 years, 8, 9, 10 years after I left Bell Labs. The structure and culture at AT&T Bell Labs, the life as a postdoc. So this guy, Doug Netelson, was a postdoc in Bell Labs during the time where Sean published all these papers. Accounts for Bell Labs' great success and most recent fractional quantum Hall effect Nobel Prize in 1998. So this happens about a year, 2 years after Bell Labs got the Nobel Prize for the fractional quantum Hall effect. They got the Nobel Prize, I think, also for the fractional quantum Hall effect. In fact, Bell Labs was really the mecca for solid state physics for many, many years. The first transistors was invented there. Solid state lasers, all liquid crystal displays, many important development in nowadays technology really started there. When I went to do my postdoc at Bell Labs, it really was considered as a mecca for solid state physics. It was a very, very special place. Everybody wanted to get there. It was very difficult. It was a great advantage for people to develop career. You could go there, do a postdoc. If they liked you, they would hire you as MTS. MTS is a member of technical staff. So you're a scientist. You get unlimited funding. You have to justify, but you don't need to write grants. You do your research and publish. And after a few years, you build your name and you can go to universities and get already a tenure position. So it was a way to bypass tenure track. And it was a very, very lucrative place to go and do solid state physics. So Sean comes to Bell Labs as a postdoc, but during the late 90s, Bell Labs starts to kind of decline because of all kinds of issues. In the late 80s, the Supreme Court at the US decides to break Bell Labs. Bell Labs until then was a monopoly since Alexander Graham Bell, the invention of the phone. The Bell company was basically in charge of telecommunication. It was a monopoly. They made a lot of money. They made so much money that they allowed themselves to put 4% of their gross income into basic science, and they did not care what scientists used to do. They just gave money for people. They hired the best people, and they knew that the best people would do good science. Even if it's not relevant directly to telecommunication, it would be good, and developers will benefit from this. To that extent that the director of Bell Labs, when I was there, got his Nobel Prize for the discovery of the infrared background radiation following the Big Bang. So it was Penzias, and they really allowed people to go far and wild. There was a group in Maryhill working on brain research in birds, really remote concepts from telecommunication. The environment was really fantastic. You definitely did the best science over there. So Sean joined this, but at the late 90s, after the Supreme Court decides to break Bell Labs into 7 baby bells, and Bell Labs, AT&T Bell Labs, the laboratories themselves changed name, they call themselves Lucent, and less money goes in, and things basically start to decline. I first met having Sean a couple of months into my postdoc. Sean had come to Bell Labs as a postdoc a few months before me and was working with Batlog, who was also a head of the materials physics department. When I met Sean, he was a quiet, nice guy who I would say hi to in the hall at some rate. He was working in a lab downstairs from Willett's lab, down and across the hall from communal printer room. He was of medium height, with sandy curly hair. And at the time, all I knew was that he was one of the group of people who would play soccer for a bit on the field outside by the helipad after lunch some days. So basically a nice guy. Batlog was a very respected scientist, an Austrian with a graduate degree from ETH Zurich. Batlog had done work on a whole variety of strongly correlated materials. And bear in mind that there was a fierce competitive, secretive streak to many who came up scientifically through the high TC craze. So this is about the time that the Hall effect was discovered, the fractional Hall effect was discovered, and people were coming almost every day with new high TC materials, raising the temperature to, usually it was heat and liquid helium. And during the 90s, people started to discover new materials with higher and higher TC. So there was really a competition and a craze. And this guy is operating during these times. The potential stakes were enormous if someone could discover a very high temperature superconductor with useful properties. As time went on, it was an open secret that now that his kids were out of school, Batlog was looking to move back to Europe and had been working on securing a senior position at Zurich. As a result, he was traveling quite a bit and was less of a visible presence. And somewhere in there, I'm pretty sure the department leadership was reorganized in advance for his planned departure. So basically, this guy, Sean, comes to work with his mentor, Batlog, but Batlog is considering basically going back to Europe. Just a second. Okay. The materials in question were waxy and brittle, and making good contacts between metal electrodes and this molecular system was a bit of black art. Anyway, data appeared, papers began to be submitted by Sean and company and appearing in print. So basically, Sean is trying to develop cheaper electronics. He's using molecules instead of silicon, and he's using these waxy, brittle materials. And there is some black art associated with this. So this is a background for what we are going to discuss today. Getting a paper out of Bell Labs was supposed to be more difficult than in a university. Draft paper was then sent to someone else in the division, not directly connected with the work. I myself experienced this when you wanted to publish out of Bell Labs. Before sending the paper to a journal for peer review, you would actually have an internal peer review, And only once you pass the internal peer review, then it would be sent to the journal. So in principle, it should have been very difficult to publish papers out of Bell Labs. Nonetheless, Sean papers are published. And we'll soon see how many of them and at what rate. By late 1999, Sean had been apparently quite productive, producing half a dozen papers over about a year and a half, looking at electronic properties of devices based on clock single crystal. So he had a collaborator, his name was Clock, and this guy basically made all the molecular crystal that Sean was using in his devices. It sure looked like these materials were going to lead to great things, as the reported results indicated mobilities in the hundreds. So you might be familiar with silicon, doped silicon. You can get very, very high mobilities, and basically all the electronic industry is based on this. But the idea was to take molecular crystals or organic molecules in foams. Nowadays, people are able to do quite a bit with wearable electronics on organic electronics. But at that time, that was just the beginning, and he was reporting mobilities that nobody else could see in those molecular systems. And climbing with decreasing temperature, an indicator of clean band-like transport. Basically, the claim was that their materials are so good, they are working like inorganic semiconductors. These positive material properties and Sean's impressive productivity combined with Batlog's endorsement were enough to net Sean a staff position. So this was really what people were very much hoping for. If you came to Bell Labs, you got a postdoc position, and if after a year or two you did well, somebody in the department would go and try to hire you as a staff scientist. And indeed, Sean was hired as a staff scientist. Transitioning from postdoc to a full MPS, by this time, the lab had reorganized and Sean was in Roger's department. Because Backlog was about to leave, he changed department heads and he moved to the Roger department. By summer of, I'm having here some difficulties with this bar. Okay, by summer of 2000, the hiring decision looked like a very good one, as Sean had published a science paper and a Nature paper in January and February, respectively, on comparatively conventional semiconductor devices based on crystal of pentasyn. In April, he published a science paper reporting field effect modulated superconductivity in devices based on molecular crystal C6. Then something even more extraordinary happened. Sean had a paper appear in Science in June, claiming to have observed the quantum Hall effect in both electrons and holes in field effect devices based on pentasyn crystals. This was a remarkable claim for multiple physical reasons. Still, the claimed device performance was amazing. This was also a shock within my part of Maryhill because this result appeared out of the blue in Science with seemingly no one knowing about it until publication. None of these people had seen the paper before it had gone out, nor had Sean or Backlog, traveling a ton during that time, given an internal seminar talk about it. So that I told you, you had to go through an internal peer review, and usually you would give a seminar to your department members on your results before those would go out. But these papers apparently were in print without anybody in Bell Labs knowing about them. During that fall, the Sean bombshell results started to flood the literature at a rate that even then should have been realized as absurd. After this, Sean really ramped up the pace. There was a science paper in July about electronically driven organic laser with a collaborator and organic electronics expert as a co-author. Not just a light emitting diode, mind you, but a laser. In November, there was a follow-up science paper with the same author list reporting a light-emitting organic field effect transistor. November also saw the published claim that with Hall carriers rather than electrons, again, a crazy high charge density, C60 could superconduct with a transition temperature as high as 52 K. This doesn't even count the additional 8 papers that year in journals like Advanced Materials, Applied Physics Letters, and Synthetic Metals. This should have raised red flags for many people if someone was actually keeping track. It's a level of output that is simply absurd for someone who was allegedly functioning as basically a one-person research group. At Bell Labs, if you were a member of technical staff, you usually had one technician and maybe one student. But he did not have a technician or a student. So basically he was supposed to go into the lab, do the experiments, and publish all this work by himself. Sean did not have a technician, he did not have a postdoc, he did not have visiting grad students. How was he actually able to fabricate devices, supposedly involving transatlantic travel for the dielectric deposition? So one of his claims in the paper that he had a better way of making contacts to these molecular crystals than anybody else. He was using some sputtering machine in University of Constance in Germany. So he was supposed to get those molecular machines from a collaborator in Bell Labs, go to Germany, prepare the contacts, come back to Bell Labs, continue doing experiments and so on. And measure all of the things, get publication quality data, analyze data, write a manuscript at this rate. Patrick had transitioned to RTR full-time in September 2000. Sean published along with co-author chemist Denan Bao another Nature paper in October, this one claiming to have made field effect transistors in which the channel was a self-assembled monolayer of molecules. This was followed up by the Science paper in December, this one claiming that by substituting molecules into the monolayer, it was possible to discern field effect transport through individual substituent molecules. So basically, he's moving from molecular crystals to monolayers of organic molecules and all the way to dopants of single molecules and claiming that basically he's doing a single molecule transistor. When I saw this paper, I pretty much could not believe what I was reading. The big APS March, APS is the biggest American Physical Society meeting in March usually, where all physicists get together once a year. So the big APS March meeting of condensed matter and materials physicists was in exotic Indianapolis that year. At the meeting, there were all kinds of stories flying around. That Sean and Bartlog had been nominated for the Nobel Prize. That Sean had been offered a big endowed professorship in Princeton. That Sean was being considered for a Max Planck directorship. This is, by the way, I don't know if you are familiar with the German academic system. A directorship at the Max Planck is really an amazing position. You don't need to write grants. You get this huge budget. You have a whole department under you with many technicians, students, postdocs, all paid for, and lots of money for equipment. So getting a Max Planck directorship at that very young age was very, very unusual. At the same time, no one had been able to reproduce any of the results, even the ones that did not seem to require exceedingly high carrier densities. So basically, his papers were so amazing that everybody tried to repeat his results. And my very close friend, we'll talk about him later on, Paul McEwen, was at Berkeley at that time and transitioning to Cornell. He was trying to repeat those measurements. He was building such transistors, and everybody in this field of molecular electronics was trying to reproduce with no success. Sean, however, claimed spectacular on-off behavior far beyond anything achieved thus far with organic materials. His measurements, in most cases, confirmed very theoretical predictions. The findings were published in prominent scientific publications, including journals like Science and Nature, and gained worldwide attention. However, no research group anywhere in the world succeeded in reproducing the results claimed by Sean. In 2001, he was listed as an author of an average of one newly published research paper every 8 days. Just think about this. The guy publishes a new paper every 8 days. In that year, he announced in Nature that he had produced a transistor on the molecular scale. The implications of his work were significant. A key element in John's claimed successful observation of various physical phenomena in organic materials was in the transistor setup, specifically a thin layer of aluminum oxide, which John incorporated in the transistor using lab facilities of University of Constance. So he was claiming, I'm doing something better than anybody else because I can put a very thin layer of aluminum oxide at a quality that nobody else can. And this is why I have better devices than everybody else. Also, the equipment and materials used were commonly used by laboratories all over the world. No one succeeded in preparing aluminum oxide layers of similar quality as claimed by Sean. And it went beyond science. BBC and many other, general public news media started to report of this achievement. Tiny transistor break new limits. Bell Labs scientists usher a new era of molecular scale electronics. Tiny organic transistors may lead to less expensive and more powerful chips. The molecular scale transistor that we have developed may very well serve as a historical bookend to the transistor legacy started by the Bell Labs in 1947. That's, at that time, the director of Bell Labs, Federico Capasso, is now professor in Harvard. Superconducting plastic, gate-induced superconductivity in solution process organic polymer foam, pressed electrically pumped organic laser. So here you see the collaborators, the organic chemist, Anand, Bao the chemist, and Klog who made the molecular crystals, and you see the picture of Sean on the right. Magic hands. As I told you, one paper every 8 days, 25 co-authors, 6 patents filing, numerous international awards. Here he gets an award, this is shown here, gets an award, it's called the Braunschweig Prize in 2001. The guy is getting famous, not only in the scientific arena, but basically everywhere. This is the annual report of Lucen Bell Labs in 2012, going to the shareholders. So he highlights that report. Sean and Bao teamed with Meng to fabricate molecular scale organic transistor. The work sets the stage for a new era of easily assembled and potentially inexpensive molecular electronics that may prove an alternative to silicon-based electronics. So basically, Bell Labs tell their investors, you're going to get rich because of this guy. But at the same time, the company is in trouble. There was some internal trading, and stock commission looks into this, and suddenly the stock goes down, and there are all kinds of issues. So here, Lucen had to pay $25 million to the commission based on the commission settlement. And this is really the downhill of Bell Labs. This is happening during this time. All right, so this basically just as somebody can turn off the mic. There is some noise. Okay, thank you. No, it's still on. Okay, so I want to emphasize the story I'm telling you today took the field of molecular electronics decades back. It had such a huge impact. Nowadays, you might know that there is a lot of really good work with semiconducting polymers. And in fact, all the ideas that Sean had are putting into practice nowadays. But because of the Sean scandal, this work was really put aside for many, many years, and we are going to try to understand why. Any questions so far? All right, let's move on. So the story is interesting. At some point, obviously, everybody's trying to reproduce this data and they cannot. And they start to look into the data more carefully. So soon after Sean published his work on single molecule semiconductors, others in the physics community alleged that this data contained anomalies. Julia Zhu and Lin Lu originally noticed issues with Sean's paper describing the assembly of molecular transistors while attempting to patent research on lithography, realizing by accident that Sean had duplicate figures. So these are two scientists in a different field trying to write a patent on some development in lithography, and they want to cite in the paper, in their patent application, previous works. One of them is Sean's paper, and they notice some image that is duplicated, and basically they write it down somewhere, but they don't. There is no suspicion of misconduct; it's just a mistake. Zhu and Lu had attempted initial experiments to gather evidence for their patent, but relied on the scientific outcome of Sean's work. It was not until April 19, 2002, when Lu and Zhu were meeting with their patent lawyer, John McCabe, that they noticed the duplication. And at that point, another person comes into the story. Her name is Lydia Son. She was a professor at Princeton University, a very good friend of Paul McEwen from Berkeley at the time. Noticed that the two experiments carried out at very different temperature had identical noise. And one of you already mentioned this. When the editor of Nature pointed this out to Sean, he claimed to have accidentally submitted the same graph twice. Paul McEwen of Cornell University. So in 2001, Paul moves from Berkeley to Cornell. I moved from Berkeley to UCLA. But both of us kept our labs still working until the renovation in the new place was finished. And I used to go every week to Berkeley for several days, and still could see and meet and talk to Paul on a regular basis. So really a personal note for this whole story. I've shown you at the beginning of today's presentation, those graphs from different figures that I can scale, and the data looks exactly the same. At that time, we did not have PowerPoint as sophisticated, but we did have a Xerox machine with the ability to scale. I don't know if you remember, but before PowerPoint and digital projectors, we used to have transparencies as a way to present in conferences and so on. So Paul took transparencies and Xerox one figure at several different scales and overlaid this on another of Sean's paper. He called me to his office and he showed this to me. And that was quite shocking and amazing. So Paul and Linda were really the heroes of the story because they discovered, they do a lot of work, they bring it up to the community. They found the same noise in a paper describing a third experiment. More research by Paul McEwen, Lin Lu, and other physicists uncovered a number of examples of duplicate data in Sean's work. This triggered a series of reactions that quickly led Lucent Technologies to start a formal investigation. In mid-May, I got a phone call at work from Bob Willett, who told me that there were apparently terrible problems with several of Sean's papers. It had been noticed by Lydia Sean and Paul McEwen that there were clear cases of suspicious figures, relabeled in different papers, but clearly the same data replotted. To say I was shocked was an understatement, but once you actually look at the figures side by side, there is no doubt at all that there are problems. I found a few more that hadn't been pointed out yet once I started looking, and forwarded those to Don Monroe, who was serving on the hastily convened investigative panel that the labs put together. Now we switch from Doug to Lydia's own recollection. So, Son and her friends felt his data to be too perfect, with many groups failing to reproduce these potential Nobel Prize winning results. The uncovering of Sean's scientific fraud would begin with two researchers, Liu and Zhu, who noticed the duplication of figures in one of Sean's papers while preparing a patent. Around the same time, Son received a phone call from an informant who has remained anonymous, asking for Son's opinion on two figures, each in a separate publication by Sean, but both appearing to have identical notes. So in fact, Lydia got a tip from somebody. We don't know who that person is until today. And that started this really. I just happened to check my voicemail messages in my office. At that time, we still had a separate machine to record voice messages in my office. And I had a very interesting voicemail message. And it said, Lydia, this is your homework. Look at these two papers by Henrik. And by the tone of his voice, I knew something very juicy was going on. And so I quickly downloaded these two papers, one from Science and one from Nature. Son spotted that the level of noise, which she described as squiggles and bumps, was identical even at different temperatures, which cannot be possible. Noise should never overlap one another. Noise simply cannot reproduce. After discussion with others, including Paul McEwen, it was decided that Son would inform Nature of this discovery, as her acquaintance all had preprint papers under review at Nature at that time. So the people who did this investigation wanted Son to go to the journal because all the others had submissions and there was a conflict of interest. One could accuse them that they're trying to sabotage Sean's submissions because they are competing. Son informed Nature via phone call with Carl Zimmerlis, who was the editor. Even before an investigation had begun, Sean and McEwen would discover the same issue in 6 of Sean's papers, with the two remarking that they had become akin to Mulder and Scully from the fictional TV show X-Files, uncovering the extent of Sean's deception. I emailed Nature and then they contacted Sean with our claims. He replied that it was an innocent mistake and that he would provide the relevant data. But as we all worked through more of his results, everyone discovered more and more instances of what looked to be fraudulent data, and everything snowballed from there. When a colleague got in touch with Henrik Sean himself, his only comment was, how could that be? Then we sent him the PowerPoint slides presenting our case. We never heard back from him after that. All right, so I told you the story. I told you the beginning of allegations, and then there is an investigation by an official committee. In May 2002, Bell Labs set up a committee to investigate with Beasley from Stanford as a chair. The committee obtained information from all of Sean's co-authors and interviewed the 3 principal ones, Bao, Batlog, and Clog. It examined the electronic drafts of disputed articles, which included processed numeric data. The committee requested copies of raw data, but found that Sean had kept no laboratory notebooks. His raw data files had been erased from his computer. And according to Sean, the files were erased because his computer had limited hard drive space. In addition, all of his experimental samples had been discarded or damaged beyond repair. Sean acknowledged that the data were incorrect in many of these articles. He claimed that the substitution could have occurred by honest mistake. He omitted some data and stated that he did so to show more convincing evidence for behaviors that he observed. So basically, no way to reproduce anything that he had done. There were no lab notebooks. There was no raw data saved anywhere. And you could not even get any old samples to go and do measurements on those old samples again. So this is the first page of the report by the committee. comes out in September 2002. It's a pretty long report. Here is the table of content. And obviously they start with this image that I showed you. And here they basically analyze. So you see here in open circles and open triangles in green and red respectively, and you see dots, and those are the two figures. One is in circles and the other one is in field symbols. So basically there is one data point here manipulated and one data point here manipulated. All the rest are identical, including the noise. So this is taken from the report. Original plotting data from figure 1 and figure 2 extracted from an electronic draft, replotted to illustrate that the data present in both are exactly the same after dividing the latter by 2. So basically what Sean did was multiplying the data points by a factor of 2 and changing one of the data points. All but a few of the solid symbols are within the open symbols and agree with each other to 5 significant figures, although they represented distinct data sets. On September 25, 2002, the committee publicly released the report. The report contained details of 24 allegations of misconduct. They found evidence of shown scientific misconduct in at least 16 of them. They found that whole data sets had been reused in a number of different experiments. They also found that some of his graphs, which reportedly had been plotted from experimental data, had instead been produced using mathematical functions. So some of the data in some of his figures were not raw data. They were just calculation by a computer following a mathematical formula. The report found that all of the misdeeds had been performed by Sean alone. All of the co-authors, including Batlog, who was the head of the team, were exonerated of scientific misconduct. This sparked widespread debate in the scientific community on how the blame for misconduct should be shared among co-authors, particularly when they share a significant part of the credit. So basically, in all of his papers, Sean had collaborators. He got the molecular crystal from one guy, he got molecules from another guy. His boss was on all of the papers, and the committee comes and says, the only guy who manipulated data and did something wrong is Sean. All these other people on all of these papers are clean, they've not done anything wrong. The members of the committee were Beasley, Data, Kogelnik, Cromer, and Monroe. And from their executive summary, this final allegation can be grouped into 3 classes: substitution of data, substitution of whole figures, single curves, and partial curves in different or the same paper to represent different materials, devices, or conditions, unrealistic precision of data, precision beyond that expected in a real experiment or requiring unreasonable statistical probability, results that contradict known physics, behavior inconsistent with stated device parameters and prevailing physical understanding, so as to suggest possible misrepresentation of data. The committee's main findings and conclusions can be summarized as follows. By all accounts, Dick Sean is a hardworking and productive scientist. If valid, the work he and his co-authors report would represent a remarkable number of major breakthroughs in condensed matter physics and solid-state devices. Except for the provision of starting materials by others, all device fabrication, physical measurement, and data processing in the work in question were carried out by Hendrik Sean alone, with no participation by any co-author or other colleagues. None of the most significant physical results was witnessed by any co-author or other colleagues. Proper laboratory records were not systematically maintained by Hendrik Sean in the course of the work in question. In addition, virtually all primary raw electronic data files were deleted by Hendrik Sean, reportedly because the old computer available to him lacked sufficient memory. No working devices with which one might confirm claim results are presently available, having been damaged in measurements, damaged in transit, or simply discarded. Finally, key processing equipment no longer produces the unparalleled results that enabled many of the key experiments. Hence, it is not possible to confirm or refute directly the validity of the claims of the work in question. So we talked about the or the reproducibility crisis and the response as open science, such as scientists should provide enough information to be able to reproduce the data. None of this exists in this case. There is nothing you can use in Sean's work to reproduce his data. The most serious allegations regarding the work in question relate to possible manipulation and misrepresentation of data. These allegations speak directly to the question of scientific misconduct. The committee carefully investigated each of these allegations and came to a specific conclusion in each case. The evidence that manipulation and misrepresentation of data occurred is compelling. In its middle form, all data sets were substituted to represent different materials or devices. Sean acknowledges that the data are incorrect in many of these instances. He states that these substitutions could have occurred by honest mistake. The recurrent nature of such mistakes suggests a deeper problem. At a minimum, Sean showed reckless disregard to the sanctity of data in the value system of science. His failure to retain primary data files compounds the problem. More troublesome are the substitutions of single curves or even parts of a single curve in multiple figures representing different materials or devices and the use of mathematical functions to represent real data. Sean acknowledges these practices in many instances, but states that they were done to achieve a more convincing representation of behavior that was nonetheless observed. Such practices are completely unacceptable and represent scientific misconduct. One of the most troublesome cases in that is of superconductivity in polythiophene. Here, identical curves appear multiple times in whole or in part in a single figure. Sean acknowledges that these data are not valid, but cannot explain how they arose. In the view of the committee, it is not possible that this set of curves represent real data, and therefore, this is a clear, unambiguous case of scientific misconduct. In the end, the committee concluded that of the 24 final allegations examined, Sean committed scientific misconduct in 16, some of which were interrelated. Of the remaining 8, 2 were judged to have no clear relationship to publications, while 6 were troubling but did not provide compelling evidence of scientific misconduct. So the conclusion is there are at least 16 cases of misconduct and possibly 8 more, and maybe even more than that, but they cannot really decide on this 8. The committee finds all co-authors of Sean's in the work in question completely cleared of scientific misconduct. The committee also finds no evidence that the laboratory practices of any co-author in the work in questions are outside the accepted practices of their fields. In addition to addressing the question of scientific misconduct, the committee also addresses the question whether the co-authors of Sean exercise appropriate professional responsibility in ensuring the validity of data and physical claims in the papers in question. By virtue of their co-authorship, they implicitly endorse the validity of the work. There is no implication here of scientific misconduct. The issue is one of professional responsibility. So the question of the co-authors was a huge question. It developed to a big, big story. But at this point, the committee, the appointed committee, basically leave this question of responsibility of co-authors to the community to decide. They are not taking a position. The committee found this to be an extremely difficult issue, which the scientific community has not considered carefully. Therefore, no clear, widely accepted standards of behavior exist. In order to proceed, the committee adopted, for working purposes, a minimal set of principles that it feels should be honored in collaborative research. At its core, the question of professional responsibility involves a balance between the trust necessary in any collaborative research and the responsibility all researchers bear for the veracity of the results with which they are associated. The committee does not endorse the view that each co-author is responsible for the entirety of a collaborative endeavor. The relative responsibility of researchers with very different expertise, seniority, and levels of participation must be considered. So basically, they cannot really make a decision about the co-authors. Nowadays, many journals ask people to write what they contributed to the paper. But we are talking about 2001, 2002, and the committee basically doesn't really know what to do. The committee examined this question for each co-author, considering the nature of their participation and their differing degrees of responsibility. The committee concluded that the co-authors of findings shown in the work in question have in the main met their responsibilities, but that in one case, questions remain that the committee felt unqualified to resolve, given the absence of a broader consensus on the nature of the responsibilities of participants in collaborative research endeavors. I guess they are referring here to his boss, to Backlog, what was his responsibility. Nonetheless, they decide not to decide. So the committee gave Sean the opportunity to respond to their conclusions. So he sent them a letter with responses. And let's read his response. Although I disagree with several of the findings and conclusions in the report of the investigation committee on the possibility of scientific misconduct in the work of Sean and co-authors, I have to admit that I made various mistakes in my scientific work, which I deeply regret. Some of these mistakes might have been related to difficult circumstances and others I did not realize in time. Nevertheless, it was my responsibility and there are no excuses for these mistakes, and would like to apologize honestly for these mistakes to the co-authors and the scientific community. So basically he says there is no misconduct, but I made mistakes. However, I would like to state that all the scientific publications that I prepared were based on experimental observation. I have observed experimentally the various physical effects reported in this publication, such as the quantum Hall effect, superconductivity, ferrous materials phasing, and gate modulation in self-assembled molecules, and I am convinced that they are real. Although I could not prove this to the investigation committee. Furthermore, I believe that these results will be reproduced in the future, and if possible for me, I'm willing to work hard on this task since reproduction will be the only proof of these scientific effects. So basically says, I made mistakes in writing those papers, I mixed crap, I was careless, but nothing is really malintention. All the phenomena I reported in all the papers are real. I vouched for this, I saw this with my own eyes. And if you give me the opportunity, I'll go back and reproduce these results. Based on experimental observation, I tried to communicate the science that described the experimental findings and that I was convinced of. Although I have made mistakes, I never wanted to mislead anybody or to misuse anybody's trust. I realize that there is a lack of credibility in light of these mistakes. Nevertheless, I truly believe that the reported scientific effects are real exciting and worth working for. So again, just to reiterate, only Sean made devices, no co-authors ever witnessed an experiment, no laboratory records were kept, original data was deleted, nearly every rule of scientific documentation was violated. Okay, so that's the committee. And then what is the aftermath? What happened next? The final report of the investigation committee was issued in September and still makes a mortifying reading. The short version, despite claims in the intro that by all accounts Sean was hardworking, productive scientist, it sure looks like he never actually did any of this stuff. There were no samples, there were no data. There were no lab notebooks. So, but basically there was nothing. What about the co-authors? As for backlog, truly that is a mystery to me. In summer of 2002, when the story broke, he quickly threw Sean under the bus. The quote, as reported by New York Times in October of 2002, was, "When I am passenger in a car and the driver drives through a red light, then I'm not to be blamed." So basically, the last author of all of Sean's paper, his mentor, was just a passenger in a car, and the driver was Sean. And if Sean makes a mistake or misconduct, I'm not part of this. So that's basically how he threw Sean under the bus. Essentially, every person who at some point had nominal managerial responsibility over Sean ended up in academia in extremely prestigious position, including Backlog, who is now retired. So basically, this scandal has not affected anybody on these papers except for Sean. Circumstances at the time within Bell Labs, high turnover, corporate upheaval, enormous trust in the oversight of the immediate senior figure Backlog surely contributed to the flux of papers that flew through without normal scrutiny or an opportunity for internal reviews of concern. In September 2002, Bell Labs dismissed Sean after finding him guilty of 16 counts of scientific misconduct out of the total of 25 allegations, including the duplication, falsification, and destroying of data. Unfortunately, most of the evidence from Sean's original experiments were damaged or destroyed, and further attempts to replicate the transistor behavior failed. Raw data has been deleted. Upon use of the retraction of 28 of Sean's publications and expiring, Sean lamented for researchers who had spent time trying to replicate Sean falsified results, commenting to Nature that, oh, sorry, I'm confusing. This is Son, not Sean. Son lamented for researchers who had spent time trying to replicate Sean's falsified results, commenting to Nature that she hoped people would learn and move forward from this incident. Son claimed that she spent 6 months of work, also affecting a graduate student at the time, on basically uncovering this misconduct, despite warning that she would be outcast from the research community. So basically, senior professors at Princeton at that time advised Son not to do what she'd done. They told her that this will impact her career and she should not go after Sean. She did not listen, and she did what she did, and it cost her 6 very precious months during her tenure track, just not doing her own science, just going after Sean. First and foremost, as a scientist, and I felt that someone cannot do this to Mother Nature, I felt good knowing that I had done the right thing. So obviously, all of these papers are being retracted. So here is a list. 9 science papers were withdrawn, retracted. 7 Nature papers were withdrawn, retracted. 6 physical review papers were withdrawn, retracted. And altogether, 28 papers were withdrawn, retracted. 7 additional papers were marked as questionable. Researchers at Delft University and IBM have since performed experiments similar to Sean without achieving similar results. Even before the allegations had become public, several research groups had tried to reproduce most of his spectacular results in the field of the physics of organic molecular materials without success. Sean returned to Germany and took a job as in an engineering firm. In 2004, University of Constance issued a press release stating that Sean's doctoral degree had been revoked due to dishonorable conduct. Department of Physics spokesman called the affair the biggest fraud in physics in the last 50 years and said that the credibility of science had been brought into disrepute. So basically in 2004, the university that gave him his PhD takes it back. Sean immediately appealed the ruling, and he's going into court to battle his university because they took his degree from him. So he appealed the ruling, but on October 28, 2009, it was upheld by the university. In response, Sean sued the university and appeared in court to testify. In 2010, the court overturned the university decision on September 27, 2010. However, in November, the university moved to appeal the court's ruling. The state court ruled in 2011 that the university was correct. And then it goes to federal administrative court in 2013, eventually federal constitutional court in 2014. So it gets all the way to Bagatz, to the Supreme Court of Germany, back and forth, and all except for one level, except the university revoking of his degree. Basically, his PhD is taken away from him. In 2004, DFG, this is a German funding agency, also issued sanctions. He was deprived of active rights to vote or to get any funding. And the story was so spectacular that it made it into a book, Plastic Fantastic, How the Biggest Fraud in Physics Shook the Scientific World. This is by Eugene Samuel Wright. You can get it on Amazon. Highly regarded science journalist recounts the case of wonderkid physicist Jan Hendrik Schon, who faked the discovery of new superconductor at the world-famous laboratories. Many of the world's top scientists, journals, and experts, including Nobel Prize winners, supported Schon, only to learn that they were the victims of the biggest fraud in science. What drove Schon, by all accounts, a mild-mannered, modest, and obliging young man, to tell such outrageous lies. Bach dives into the pivoting world of science to examine how fraud perpetuates itself today. Sean's rise and fall will be an essential and fantastic account of the missteps of scientific community for years to come. So the same way he rose to prominence, popular media, of course, immediately jumps on this huge story. So there is another book here, The Dark Secret of Hendrik Schon. There is a BBC documentary on the story. And the question is, who is to be fault? Who is at fault here? Obviously, he did all those misconducts, but is there any responsibility for the people who were basically mentoring him? What about the co-workers? What about the managers? What about the journals, the peer review, the community as a whole? So who is at fault? Why something as spectacular could have happened? The scandal provoked discussion in the scientific community about the degree of responsibility of co-authors and reviewers of scientific articles. The debate centered on whether peer review, traditionally designed to find errors and determine the relevance and originality of articles, should also be required to detect deliberate fraud. What is the responsibility of the co-authors? What is the responsibility of the mentor? And what is the responsibility of reviewers? Following this scandal, the American Physical Society issued new rules stating that co-authors should be accountable for important data in papers they sign off. So this is immediately after the scandal. Here in September 2002, APS issuing some guidelines. And books, here is a guide to responsible conduct in research. This is 2009. This is from the National Academy of Science. This is following the scandal. First, researchers have an obligation to honor the trust that their colleagues place in them. Second, researchers have an obligation to themselves. Third, researchers have an obligation to act in ways that serve the public. At the end of the day, we are getting paid by the public, and we should not mislead the public. So you can imagine that such a big scandal really affected many things. And the big, beyond the replication crisis that we discussed earlier, the practices of open science nowadays and the rules how to submit papers and putting raw data and having lab notebooks and writing who is responsible for what in a paper, all of this come because of this scandal. So how, the question that I want to ask is, how do you make sure, me as a professor, you as young scientists, how do you make sure that something like this doesn't happen to you? And it did happen to me. We'll discuss this next time. So if you want to read more about Sean's scandal, there is a big chapter in Wikipedia, recollection of Lydia Son, Doug Natelson. I gave you the highlights of his recollections of the story. There are 3 YouTube video series. Here are the links that tell the story. And this is what I wanted to discuss today. Just a minute. Let me stop sharing just a second. All right. So what I would like to do now, I would like everybody to turn on your mics and just tell me what you think and how you feel after this presentation. Any comments?
I think that his supervisor was as much as blame as he is.
Well, so the excuse was that the supervisor was busy traveling, moving to another university, and he didn't do good enough job of mentoring. So anything he got from Sean, he signed off, basically. There was no scrutiny from the advisor. And let me tell you, as an advisor, you have to trust your students and postdocs.
Yeah, I know.
The whole scientific endeavor is about trust. And I trusted, I'm going to tell you my own personal story. It's not misconduct to that level, but there was a very embarrassing case for us because of a postdoc who didn't do the job properly. And at the end of the day, the PI is in charge. So how do you make sure that it never happens to you? Especially once you start.
As a professor, I think it's maybe it's impossible if that's what you're saying.
I think it's very, very hard because you don't want to treat your students as cheaters.
Yes.
You want to build trust, but you also want to build some confidence in the scientific method. But what drives people to do what Sean did? That's the main question. He truly believed that he saw these effects. And then he faked everything around this. But
how do you know he believed that he saw it?
Sorry?
How do they know he believed that he saw it? Just taking
well, at least what look, we talked about incentives. The whole system of tenure track and how people are being promoted in academia is based on publications. And we already discussed that this is the wrong incentive because we should really incentivize how to do good science rather than, how to do a lot of science and a lot of papers and getting promoted by H factor or something like this. So obviously part of this, he wanted to be famous, he wanted to get prizes, he wanted to impact the world. So he had a very, very strong drive to do this, all the way to cheating. We think about science as something very pure. And here you see the biggest case in scientific history of misconduct. So obviously he went overboard compared to everybody else. Yes, scientists are very competitive in nature. But he crossed the border in a gross fashion, and in my view, it has to be some kind of a mental disease. Most people will not do what he did. He was so convinced that, you know, he's right, he's seeing all these effects in the lab, and then it's okay to manipulate the data to show what he thought he saw in the lab.
But isn't it amazing that these incredible results and nobody was interested in actually seeing that?
Well,
in person, going into the lab and seeing the experiment.
Yeah, all of those, yeah. This is really amazing, because I can tell you on the battery side, people try to reproduce this data. How come nobody in Bell Labs? Well, he did not show them results. He sent papers for publication against the rules. You were not supposed to send papers from Bell Labs to the journals without having an internal committee going over this. So people did not know. Suddenly there were papers.
It also seems his misconducts were very unsophisticated. I mean, something which looks even 20 years ago easy to find out. So what
but how do you allow yourself to publish so many papers with so much exciting, revolutionary findings, and not thinking that others are going to try to reproduce this? And they will find your mistakes or fraud. I think that goes beyond normal behavior. I think that there is something very, very deep in his personality that allowed him to do this. But then we have to ask ourselves, yes, his colleagues in the lab should have caught him, should have walked into the lab and asked to see the experiment, asked to see his paper, asked to see his data. The peer review should have done a better job. It just showed how broken the system was that he got that far. For 3 years, he was able to publish all those amazing papers. The result of what happened. Let me just finish and I'll go. The result of what happened was that for almost 3 decades, nobody wanted to touch molecular electronics. It was tainted with misconduct and fake, and it doesn't work and so on, which is not the case. Nowadays, we have some devices, and lots of people are moving into conducting polymer type of solar cells and wearable electronics. And so he was visionary in many ways. He worked on interesting concepts, but because what happened, this science was put on the shelf for many, many years, and only nowadays people with better materials are coming back and doing this type of experiment. Yes, you wanted to say something?
Yeah, the first question that I could think of is like, how is the review process working? Because we already discussed these things, like how did they review all these things without thinking about what is going on? And
yeah, but the question is that the other side to this is, are reviewers supposed to find fraudulent science? Is this their job? Or should we trust everything that we get from authors and we'll just look into the scientific methods and try to find some errors or wrong citation or something is missing? But a priori, we assume that every scientist is an honest scientist. Is our job to find cheaters? Or we should assume that anybody who is in this business is honest? You don't think as a reviewer that whatever you're getting is from somebody who's trying to cheat.
Till now, also, we saw many papers which are reviewed the very same way, because there is no open science. So I don't know how they get published even in some reputed journals. But when you look at some basic physics of those stuff, it doesn't even make sense of how did they publish these things and who reviewed those papers.
Yeah, look, this is the scientific method is not perfect. And even nowadays, I try to bring all these cases. So the Alzheimer's case and the food supplement case, it happens all the time. Do we have enough stops and balances to discover this early on or not? And how can we do things better? So again, this is the topic of meta-science. How can we improve such that we don't experience such big scandals in the future? Yes, somebody wanted to say something.
Yes. In regards to the peer review and the responsibility of the journal itself, it is my feeling that as much lesson learned from this case, there is still something that I think still repeats even today, and that is the ease, I would say, how easy it is for a strong institute to publish, because it is Bell Laboratories, and it's so prestigious.
Yeah.
Then people check much less, and that gives him the enough credibility to publish in higher impact journals.
Actually, I brought that point several meetings ago, which is absolutely true. There are biases. So there are many things wrong in the way we conduct science. And we are trying to improve, but we don't have, the golden answer. What is the best way of doing things? We talked about replication. We talked about many issues. We talked about peer review, wrong incentives. And for me, to find so many cases of fraudulent science, even today, that's outrageous. And people think that they can go by. So what drives somebody, a scientist, what drives a scientist to cheat and think that he will not get caught? And what is a gain versus what could be lost? So how do you teach your students to be better scientists? And you don't want to be surprised as a professor by a student who is doing something like this. And I had a postdoc. I'll tell you about the story next week. It's really, there are no golden answers. It's really, I think, at the end of the day, about the personality of the mentors to train and teach students to become better scientists. This is what we are trying to do in this course. I wanted to bring all these cases to you just to consider and make sure that you are not the one to get, at least not to get caught, but hopefully not to commit misconduct. I mean, the guy was, at the end of the day, he was mentally ill, but he was also very stupid, right? He did such obvious misconduct that was, once you catch it, all of his work was trashed. His PhD was trashed, everything. I guess he already got used to manipulating data during his PhD. So even his PhD mentor has a contribution to the story.
I would say that it is nowhere a stupid mistake. It is deliberately done, very knowingly known that, okay, what I'm doing is...
Yeah, but thinking that you're not going to get caught. That's a stupid part. Yes, somebody else wanted to say something.
Have you ever seen such a thing in theoretical physics?
Yes.
Because if so, it would be very interesting.
So I ran this course already for several years, both at Bar-Ilan and at UCLA, and some students brought some interesting cases. So there was a funny, not fraudulent, but really funny paper about rediscovering calculus and the derivative, recently, like 30 years ago. So from esoteric field of doing physiology. There are some cases, but not as prevalent. I agree, it's harder to do this in theory than in experiment. But yeah, theorists, I think, would be afraid of other people finding the deliberate mistake. I mean, once you come up with some formula or something, right, it can be checked.
Yes.
How do you introduce fraud into development of a theory? What are the opportunities? Where can you commit a fraud?
That's why I ask. I cannot find any.
Yeah, it's much harder. But data, you can reproduce data, right?
Yeah.
Other thoughts?
Maybe just what you said, that an environment that allows for someone to hide his data and to make his own judgment on what he gets, in a way contributes to the thought that I won't get caught because nobody looks at me.
As an advisor in group meetings, you want to see the raw data, you want to see, discuss data and so on, and ask questions and get to the right culture. But at the end of the day, we are individuals and with different motives. And some people have such a strong drive to succeed and they're willing to do anything. And how do you stop them?
Yes, but according to what you told us about all of this case, it seems like there was even more of a chance to do it because he worked alone. Nobody looked after him. Even the co-authors didn't look after his data. In
the science of accidents and bad things that can happen, usually it takes several different factors to go wrong until you have a catastrophic disaster. Same here. It took several different factors to build the scandal to that level. So yeah, Bell Labs was in decline. The direct boss was not there. The scientists around did not pay attention because they were busy, because their environment was deteriorating. And they chose to trust this guy. He was a nice guy. He was a very nice guy playing soccer after lunch and, nice to talk to him during lunch. And nobody had the slightest suspicion that this guy might be a fraud. So they chose to believe him. It's a matter of trust. It's not that easy for you to look in the scientific arena at somebody and say, this guy is a fake, I don't trust him. It needs to build up. Our assumption is everybody who is in this business is an honest guy because, science is pure and we are going to do science the best we can. We want to promote the knowledge front and none of us is really a cheat. That's the assumption. So it's hard to find the cheaters if that's the operating consensus. So it's the biggest scandal I know. And so I really encourage all of you to find out papers you want to report. Please go ahead and find other scandals for people who have not chosen papers as of yet. I do want to hear about the Alzheimer's story. So if somebody is willing to pick it up or maybe more over once, because this is a big story. Okay, put down.
I took the Alzheimer.
Okay,
you
so
wrote it to me.
Okay, good. Just put the link of the paper in the Google Sheet that everybody knows.
Yes, I will do it. I'm sorry.
Okay.
Yes, I will do it.
And anything else? Okay, guys. So again, for next week, I'm supposed to land at 4 p.m., rent a car and come to campus. Khaled reserved us a room. What is the name of that room? Can you turn on your mic?
Yeah, it's the room in the physics building.
It's the third floor, just across from
301 in the third
just across. Floor. Yeah. So 7 o'clock in the evening, that room, and it will be hybrid. We'll turn on the computer and do Zoom as well for people who cannot arrive. But I would love to meet you face to face. I hope that travel is okay and there are no delays. If there are delays, I will let Khaled know and he will communicate to all of you. Any other questions, requests? If no, good night. See you next week. Bye-bye, everybody.
Thank you very much.